On January 17, 1991, at 2:30 a.m., the opening attack of Operation Desert Storm was set in motion. Tasked with crippling Iraq's command and control, shipborne Tomahawk and B-52 launch AGM-86 cruise missiles were employed to infiltrate targets within Baghdad. Alongside this initial inrush of deep-striking assets was a new class of weapon. This attack was the first public debut of a stealth aircraft facing off against one of the largest air defense networks in the region. The iconic Lockheed F-117 Nighthawk, the first stealth strike platform, were among the first sorties to enter the heavily defended airspace of Baghdad. Supported by standoff electronic jamming EF-111 aircraft and possessing no radar, guns, missiles, or defensive countermeasures, it relied entirely upon its ability to remain hidden from radar, to penetrate Baghdad, drop its two laser-guided 2,000-pound bombs, and egress with impunity. The success of these initial strikes, coupled with the punching of a hole in Iraq's early warning air defenses by Apache attack helicopters, paved the way for a massive bombing effort over the next 24 hours, composed of over 2,600 sorties targeting command and control bunkers, missile launch pads, equipment storage areas, communication facilities, and airfields. That night, the need for stealth was proven, cementing itself into the list of must-have capabilities of any new aircraft program. But where did this peculiar classified aircraft emerge from, and what technologies made it so stealthy? It all started in the 1960s with a Soviet physicist and his undervalued equations. In order to understand how stealth technology emerged, we need to quantify what stealth is. Stealth isn't one specific technology, but rather a mantra of design that incorporates low observability. The ability to detect an aircraft can range from simple visual and acoustical detection to more sophisticated means such as emitted radiation detection and tracking by infrared and radar. Of all the potential threats faced by combat aircraft, detection and tracking by radar pose the most risk. Radar, infrared, and optical detection all rely on the bouncing of electromagnetic radiation off an object in order to gather information from it. However, radar differs in that the source of the reflected radiation is actively emitted from the observer. With passive methods of detection, the target's own emissions or ambient light are used. Radar relies on beaming radiation out into a volume of space and analyzing the resulting reflected energy to detect and track. Aside from the source of the radiation, the wavelength of the radiation differs between detection methods. Visible light has a wavelength range of 380 nanometers for violet light down to 700 nanometers for red light. Infrared light occupies the wavelength range below that, between 700 nanometers and 1 millimeter. Below this is the realm of radar, the region of the spectrum known as microwaves and then radio, ranging from 1 millimeter all the way to 3 meters. While detecting an aircraft provides a warning, in order to defend against it, it must be tracked. Tracking is the determining of a target's position, velocity, and heading from a reflected signal. A tracked aircraft is in effect targetable by missiles and anti-aircraft artillery. Smaller wavelengths allow for more resolvable detail, making tracking easier, but this is compromised by range. As a general rule, the smaller the wavelength, the higher the atmospheric absorption and attenuation of the wave. While some air defense weapons can track optically, infrared tracking is the predominant method for close-range air defense due to its ability to see the heat of an aircraft through the atmosphere. Infrared tracking works by using an infrared sensor similar to a camera to look for the highly contrasting signature of hot jet exhaust gases and the warm aircraft body against the ambient air temperature. Because of atmospheric absorption, infrared radiation can only be used for tracking at short distances, typically 20 miles or less. Infrared homing weapons are usually found on short-range anti-air missiles mounted to vehicles or in shoulder-launch systems called man-pads or man-portable air defense systems. The Stinger missile is a commonly used example of this. In contrast, the longer wavelengths of radar detection and tracking are what makes it so powerful. Its ability to penetrate the atmosphere at much further ranges. The first military use of radar began around the start of World War II. One of the more notable uses was in the air defense of England. By 1939, a chain of radar stations protected the east and south coast, providing early warning to incoming aircraft. This early radar operated on the longer wavelengths of radio and offered very coarse information on incoming contacts. That same year, a breakthrough in research resulted in the invention of the resonant cavity magnetron. This allowed for the generation of shorter wavelength microwave radiation at large amounts of power. More detail can now be assessed about the target, such as its heading, altitude, and velocity. Practical tracking radar was now possible. Fast forward to today, and most military airborne radars, including those found in radar-based anti-air missiles, operate in the 5 cm to 1 cm wavelength microwave range, as it provides a good compromise between range, resolution, and antenna sizing. At these wavelengths, tracks at distances of about 50 to 80 miles are possible. It should be noted that wavelengths from 5 cm to 30 cm are also used on ground-based early warning radars that can track targets up to 250 miles away. With a proper radar track, a firing solution can be determined, with only evasion, electronic jamming, and the dispensing of radar clouding countermeasures known as chaff offering any form of defense. Because missiles are effectively guided rockets, they have limited amounts of energy available to them to maneuver. If the target can deplete this energy before it is within detonation range, or obstruct the missile's ability to maintain a radar track, the missile can be defeated. This is known as going defensive in air combat. The goal of radar stealth is to both mask an aircraft from being detected, tracked, and fired upon from a distance. This is known as beyond visual range engagement. As distances close, radar-based engagement may transition into infrared-based targeting, either low to the ground or among adversarial aircraft within a dogfight. While the radar energy from air defenses can be detected, infrared homing missiles are particularly hazardous to combat aircraft because they offer no warning of being tracked. The only indicator of an infrared homing missile launch is through visual identification, though newer fighters such as the F-35 employ external sensors that attempt to detect launches. Defending against infrared missiles involve a combination of evasive maneuvers and deploying flares designed to mimic jet exhaust, distracting the missile's seeker. However, due to the use of sophisticated signal processing in modern heat-seeking missiles, the efficacy of infrared countermeasures are reduced. Because the reflective behavior of radar isn't as intuitively obvious as optical properties, early attempts at stealth were based on observations of radar on existing designs. It was discovered early on that the shape of an aircraft determined its visibility to radar, its radar cross-section, or RCS. For example, the 1960s-era British bomber, the Avro Vulcan, was observed to have a peculiarly small radar cross-section despite its large size, whereas the similarly sized Russian Tupolev 95 long-range bomber had an extremely prominent radar cross-section. Other observations pointed towards the internal construction of the airframe. Certain configurations of internal structure can trap radiation, causing reflections between internal faces until the energy dissipates. This pseudo-stealth technique was implemented on both the A-12 and the SR-71. While these observations pointed designs in the right direction, for truly effective stealth, a better understanding of radar diffraction was needed. The first steps to overcoming this technological hurdle occurred in 1964. That year, Soviet mathematician and physicist Peter Ufimtsev published a paper titled Method of Edge Wave in the Physical Theory of Diffraction in the Journal of the Moscow Institute for Radio Engineering. Extending theoretical work published by the German physicist Arnold Sommerfeld, Ufimtsev's paper demonstrated the first major breakthrough in the understanding of radar wave behavior. Ufimtsev's conclusion was that the strength of the radar return from an object is related to its edge configuration, not its size. His paper also demonstrated the ability to calculate the radar cross-section across a wing surface and along its edge. The implications of this discovery was that even a large aircraft could reduce its radar signature by exploiting these principles. Astoundingly, the Soviet administration considered his work to have no significant military or economic value, allowing it to be published internationally. During that time period, Lockheed's elite Skunk Works design team was working on a stealth proof-of-concept demonstrator called HAVBLUE. The engineering team struggled with predicting stealthiness as the program they created to analyze radar cross-sections, called Echo 1, failed to produce accurate results. Dennis Overholser, a stealth engineer on the project, had read Ufimtsev's paper, realizing that he had created the mathematical theory and tools to do a finite analysis of radar reflection. Ufimtsev's work was incorporated into Echo 1, allowing for more refined and accurate results. Despite the objection of Skunk Works director Kelly Johnson, the faceted design was chosen due to its predicted effectiveness. The iconic early stealth look was a direct byproduct of the computational limits of computers of the time, which limited Echo 1's ability to perform calculations on curved surfaces. Wooden mock-ups covered in metal foil were constructed and subsequently tested for radar cross-section, confirming Echo 1's predictions. Its stealthiness was attributed to its difficult-to-construct faceted body, jagged edges, use of a wing sweep angle of 72.5 degrees, and inward-canted vertical tails. Known as an edge-aligned planform, the matching set of angles of the overall shape worked together to reduce radar cross-section. This worked by reflecting and dispersing radar energy away from its source, making it difficult to detect and track. In addition, a simultaneously developed radar-absorbent material was applied to the aircraft's flat surfaces. Special coatings were also applied to the windscreen, giving them metallic characteristics. To reduce its infrared signature, non-circular tailpipes were used to minimize the exhaust cross-sectional volume and maximize the mixing of hot exhaust gases with cool ambient air. It was also made subsonic to prevent detection by sonic boom. It was discovered that rotating components of a jet engine increases radar observability immensely. To counter this, the engine inlets were mounted on top of the wings, with the engine inlet being covered by a low radar cross-section grid. During takeoff, top-mounted inlet doors would open to allow more airflow. Because stealth was of the highest priority, the shape of the aircraft made it inherently unstable. A quadruple redundant fly-by-wire control system borrowed from the F-16 was integrated into the aircraft to give it normal flying characteristics. Despite the loss of both demonstrator aircraft, the aerodynamics and combat usability of the design was further refined. The aircraft was scaled up in size, larger engines were installed, and 2 internal weapons bays were added. The F-117 Nighthawk was born from these changes, reaching fully operational status in 1983. It was deployed in the 1989 US invasion of Panama, but its capabilities were truly put to the test in Operation Desert Storm. Because the F-117 diverted radar energy away from its source, it was still possible to detect it using passive receivers located at different angles from the radar source. Additionally, its shape was so critical to its stealth that opening the weapon bay doors and not retracting antennas on the surface of the aircraft would significantly increase its radar cross-section. Because of this, operational tactics played a large part of the stealth equation. Missions were designed around avoiding known vulnerabilities. This reliance on tactics to mask its flaws would prove disastrous on March 27, 1999, during the NATO bombing campaign of Yugoslavia. During sorties, F-117 would routinely perform checks of weapon bay doors as they ingressed to their targets. Because opening the weapon bay doors would increase the radar cross-section momentarily, this was noted by Yugoslavian Army air defense operators. With this knowledge, anti-aircraft missile batteries were placed at advantageous positions, and their radars configured to use longer wavelengths than the F-117 were designed for. The combination of these factors allowed for the successful detection and subsequent shooting down of one of the stealth aircraft. Because the aircraft crashed mostly intact, the event was a blow to the US stealth advantage, as the wreckage was reportedly sent to both Russia and China for reverse engineering. By 2008, the F-117 was eventually retired due to its aging design, costly upkeep, and being superseded by newer generation of stealth aircraft. As the Have Blue program progressed, Northrop began working on a technical demonstrator of its own, known as Tacit Blue. Tacit Blue attempted to demonstrate a series of then-advanced technologies, including forms of stealth that employed curved surfaces and the use of less radar-reflective composite materials. During the late 1970s, due to the success of the Have Blue and Tacit Blue programs, momentum was building for the development of a deep-penetrating stealth bomber. By 1979, the highly secretive Advanced Tactical Bomber program was started, under the code name of Aurora. With the recent development of more advanced supercomputers, superseding what was available during Echo 1's development, more complex radar cross-section calculations could be performed, allowing for the design and analysis of blended curved shapes. Northrop would eventually win out as the best design choice with their flying wing design. With no protruding vertical surfaces, the flying wing design forms a near-perfect stealth shape, offering no angles to reflect radar with. An added benefit to this design is the inherently small visual silhouette of the airframe, creating visual stealth as well. Adding to this, the majority of the aircraft was made of radar-absorbing carbon graphite composites, with parts being covered in radar-absorbing materials. Internal structures of the airframe are also designed to trap radiation. Similar to the F-117, the engines were buried deep within the frame, hiding highly reflective rotating engine components. To reduce its infrared signature, the engines are mounted above the wings, masking the exhaust. Additionally, cool air is injected into the exhaust flow, further reducing its heat signature. Circulating cooled fuel is also used to cool exhaust sections of the aircraft, as well as leading surfaces of the aircraft that are heated by air friction. Additives are also dispensed into the exhaust stream in certain conditions to eliminate contrails. Designated as the B-2 Spirit, this flying wing design also offered efficient aerodynamics, giving it a range of 6,000 miles. However, with no vertical surfaces, it requires fly-by-wire computer control to maintain stability. The B-2 became fully operational in 1997, with its combat debut occurring in 1999 during the Kosovo War. Its stealth and incredible range has allowed the B-2 to take part in some of the longest bombing missions ever during Operation Enduring Freedom, with some exceeding 70 hours of flight time spanning the planet. To this day, it remains the stealthiest aircraft ever produced. While the F-117 was designated as a fighter, both it and the B-2 were exclusively penetrating bombers with no air-to-air capability. This narrow use of stealth technology would soon change. During the early 1980s, the Air Force would put forward a request for a new generation of air superiority aircraft, with stealth being a priority on the list of requirements. Unlike a bomber, the demands of a fighter aircraft are more intensive. They require speed, maneuverability, and powerful radar and sensor packages. These requirements all compete against stealth within a fighter design. Because of these compromises, stealth implementation in a fighter isn't about complete stealth, but rather being the first to detect and fire on a target. The F-22 was designed to be fast and extremely agile in air-to-air combat, utilizing powerful, supersonic-capable thrust vectoring engines and traditional control surfaces. It carried over low radar cross-section design cues from previous stealth programs, utilizing edge-shape refinements, a coated canopy, buried engines with masked inlet design, composite construction, radar-absorbent materials, and internal weapons base. Low radar cross-section was given a higher priority at angles in which it would face off against other aircraft, hindering easy detection and missile tracking. In addition, its stealth surfaces were designed to evade the smaller wavelength radar used by other aircraft. It also relied less on radar-absorbent material due to their higher maintenance requirements. Tactically, the F-22 makes use of sensor fusion, linking battlespace data from other aircraft and non-emitting sensors to avoid giving away its own position by radar emission. Overlapping with the F-22 program, work started on the F-35 stealth fighter in 1992. Design cues and technology from the F-22 made its way to the F-35. Similar techniques were employed for reducing radar cross-sections. Notable differences are the use of stealthier chines instead of leading-edge extensions for enhanced maneuverability, a wide duct engine inlet that masks rotating components, and the use of more durable radar-absorbing materials. Similar to the F-22, more focus was given to the radar wavelengths used by other aircraft and missiles. With the success and dominance of the US stealth program, the technology has worked its way into other applications. The cancelled Comanche RAH-66 reconnaissance helicopter, for example, was an attempt to employ stealth on a rotary wing aircraft. Other examples include naval programs such as the Sea Shadow and the USS Zumwalt. With unmanned aviation becoming the next frontier of combat aviation, stealth technology is also being incorporated into the next generation of unmanned air combat vehicles, as seen by the Grumman X-47B. With heavy air defense research being funneled into the detection of stealth aircraft and the emergence of competing stealth platforms on the world stage, The constant battle to stay one step ahead of detection will always be coupled to combat aviation.